I am happy to introduce Andras Recski, who will speak about interval graphs with applications.
Thank you, Andrea. Thanks for the possibility of giving this talk. I also hope that this is the last talk before lunchtime, and probably it was your Freudian slip because you wanted to have lunch already. Unlike the previous lectures, which had deep results in graph theory, the results that I am going to talk about are not very deep from the graph theoretical point of view. I want to make emphasis on the applications. And basically what I need in graph theory is just some very basic concepts. First of all, of course, I'm speaking mostly about vertex coloring of graphs, and I denote by high the chromatic number. We know that a trivial lower bound for the chromatic number is the Clique number, that is the maximum number of vertices which are determine a complete subgraph, and this number is denoted by omega, which is an obvious lower bound for height. And this may be less than the chromatic number. The simplest example is a cycle of length 5, where the Clique number is 2 and the chromatic number is 3. And of course, as you all know, there is a very important concept of graph theory, the perfect graphs, where not only high equals omega, but it is also true for every induced subgraph. This is just an illustration about induced and non-induced subgraphs. These are trivialities, but I don't have to repeat. Now, a very special case of perfect graphs are the so-called interval graphs. So suppose that you are given a set of a collection of intervals. These will correspond to the vertices of a graph. And if two intervals have a non-empty intersection, then the two vertices will be connected by an edge. So for example, in this case, the first interval is intersecting everything except the second one, and accordingly, the vertex 1 is connected to everything except the second vertex. This is a well-known construction, and graphs which arise in this way from some sets of intervals are called the interval graphs. Tibor Gallai, famous Hungarian mathematician, was the first who explicitly proved that every interval graph is perfect, although he didn't use this expression at that time, because this result is earlier than the definition of perfectness, as far as I know. Now, it's well known that usually the question of deciding whether a graph is colorable by 3 colors is an NP-complete problem, or NP-hard problem. But in case of interval graphs, this can be solved in linear time, and as long as P is not necessarily equal to NP, this is a very important contribution. Now, these very easy results that we were talking about have very important applications in the design of very large-scale integrated circuits. In order to continue the things, I need a few definitions from VLSI technology. So these are not pure mathematical definitions. The typical chips that you are finding in almost every electronic equipment contain a lot of building blocks which are put on boards, isolating boards, and the points where the devices are meeting the board are the terminals, and you want to connect certain pairs or other subsets of terminals by wires. That's the way how you are wiring a board. And theoretically, the location of the terminals can be anywhere, but the two most frequent geometric arrangements are the so-called channel routing problem, where the terminals to be interconnected are on two parallel sides of a rectangular grid, or the switchbox problem, then you have again a rectangular grid, and all the sides may contain terminals. And if I speak about nets, that means subsets of terminals which have to be interconnected, I simply use the notation that elements of the same net, I mean terminals which belong to the same net, will have the same number. So for example, in the channel routing problem on the right hand side, I have two copies of 1 on the northern side and one copy of 1 on the southern side. It means these 3 points have to be interconnected somehow. And of course the wires which are interconnecting these 3 copies of 1 must be disjoint from any wires used by other nets. That's the basic problem. Of course the question is, what is the technology? How can you route these wires in practical situations? Of course, there are two problems from the mathematical point of view. If you are given such a specification, the most important thing is whether you can route it at all. And if yes, then in case of channel routing, the second most important problem is how to do it in minimal width. That means, if you have the two parallel lines of the channel, you like to use as few distance as possible. In case of the switchbox routing problem, there is no such minimization problem because the geometric dimensions of the building blocks decide the size of the switchbox. Then of course there are a lot of other possibilities to minimize, for example the number of layers or total number of wires or whatever, but I am talking only about these two questions. So first of all, there are two types of technologies how you can solve such a problem. The most well-known technology is if you have two parallel layers and one of the layers is preserved for the horizontal wire segments and the other is reserved for the vertical wire segments. Here red is vertical and blue is, here red is the horizontal and blue is the vertical one. And it's very important to see that if I make a 90-degree turn from here to here, then in this point I actually have a wire hole where the electric sign goes through the board from one side of the board to the other one. And in this way, this is a possible solution of that problem that I projected earlier. Here you can see that all the vertices of identical digits, that means all the terminals belonging to the same nets are interconnected, and there is no short circuit because if you see a horizontal and a vertical wire piece, they are actually on different layers, so they don't have common overlap. This is very easy. A much more complicated technology is what we shall call unconstrained routing, when again you have two layers, or later more layers, but both of the layers may contain wire segments of both directions, horizontal and vertical. In this example, for example, if you take terminal 2, it starts going in a horizontal wire segments and turns to the south on the same layer. And of course, the red line of the net 4 can use the same corner because they are on a different layer. So this is the other technological possibilities, the unconstrained routing. Of course, I want to emphasize that this distinction between Manhattan routing and unconstrained routing is purely technological. On the other hand, what I mentioned previously, that we have channel routing and switchbox routing, are purely geometrical, only about the location of the terminals. It is not necessary that I give a Manhattan routing example for the channel routing problem and an unconstrained routing solution of the switchbox routing problem. I could have made the other two combinations as well. Now, one more thing, I mentioned already the role of the wire when you move to one layer to the other. Usually it was called wire hole at the time when we had this two-layer routing. Nowadays technology permits more than 2 layers, and then it is not a hole anymore. So for example, in case of 4 layers, it's pretty much possible that you have a small section moving from the first layer to the second layer. This is used by one of the nets, and the other small piece is used by an entirely different net. So this is the most general situation in case of more than 2 layers. Okay. the most special geometric input is if all the terminals are on the northern border of the channel. This is a very, very special case of the channel routing problem. Everything is upstairs. And in this case, everything is solvable in 2 layers using the Manhattan technology, and everybody could guess how to do that. The simplest solution is if you simply use a separate horizontal line for each net on one side of the layer, that is what I indicated by dotted lines, and you reach the corresponding horizontal wire segments by vertical layers, vertical wire segments or continuous lines on the other side of the board. That can be done, and this particular problem has been realized with width 6. But of course you can do it better. You can have solved, here you can see the solution of the same problem using only width 3 rather than width 6. I mentioned to you that the first problem is whether it can be solved at all, and if yes, then the second problem is try to minimize the area. That's the typical thing in electronics. Now, you might ask the question whether it is possible to make it even smaller than 3, and obviously you can't. The easiest explanation why you can't is that if you consider this vertical dotted line, it separates 2 terminals of net 1 and 2 terminals of net 2 and 2 terminals of net 3. Therefore, there you need actually 3 different horizontal lines to cross this dotted line, which shows that this 3 is a lower bound for the width of this solution in a Manhattan model. And theoretically you can imagine the same thing. You take an arbitrary vertical line. Each of these vertical lines has such a number that I will call density, and then the maximum density is a lower bound for the minimum width. And if you associate, now I return back to the interval graph concept that I started with. Since the original problem is to realize these connections by intervals, simply you associate a vertex to each net, and you interconnect 2 vertices if the 2 nets can't be realized on the same line because they intersect. And then such a solution, what I indicated here, is actually a coloring of the interval graph. The first horizontal line contains interval 1 and 6, and therefore interval 1 and 6 can be colored by the same color, say red. The second line here contains net 2 and 4, and therefore the vertices 2 and 4 can be colored by the same color blue. And then third line for green. So this is the point where electric engineers were very happy to understand that graph theory is something serious and useful thing, because actually every solution of this problem corresponds to a coloring. Every density of a vertical line corresponds to a clique. And the obvious observation that even an electric engineer recognizes that the maximum density is the lower bound for the minimum width is simply a reformulation only for interval graphs. The clique number is the lower bound for the chromatic number. No surprise that all these things have been rediscovered by electric engineers several times. They didn't know about Galilee, but they give a linear time algorithm to prove the perfectness of the interval graphs, simply in the following way. They use what they called left edge algorithm, a kind of greedy algorithm for really arranging the intervals in as few copies of horizontal lines as possible. Take the leftmost, take the leftmost interval and put it to the first line, and if there is some space thereafter in the remaining part of the first line, then put a second interval there. And if you have a choice of selecting several intervals here, because there are several nets which start completely to the right from the end of the realized interval, then take the one which starts as early as possible. A very natural and greedy solution. For example, in the second line, and when you are done, then you start a new line with the leftmost still unplaced interval, and then instead of taking this one, you take the other one because it starts earlier. So this is a wrong step. Instead of that, you should have selected this line, this interval to the second line. Otherwise, if you put this one to the second line, then this small area would be lost forever. And in this way, you finish the algorithm, and you finish the placement of the intervals, and how can you prove that this is the best possible? Once you are done with packing all the intervals, then concentrate on the last line, concentrate on the first interval of the last line, and take 1/2 unit step after the beginning of this interval, and take that vertical line. And obviously, this vertical line must intersect the interval in every previous line due to the greedy rule. Which means, it must intersect the interval in each previous line as well. And in this way, we have a coloring of colors and a clique of size k, which proves the theorem. So,
Is it how Galilei proved it also?
Galilei also proved it basically the same way, but this is the way how electric engineers also rediscovered it. So that's what I mentioned, and just as a curiosity, I mentioned that in graph theory we are teaching in elementary classes a lot of theorems like max-flow mean cut or something like that, speaking about minimum cuts. Here we are interested in the maximum cut, namely about the cut which intersects the maximum number of intervals, or I would say the worst of all the cuts. And in this respect, it's interesting to mention that this has been already discovered by Shakespeare, you know, in Julius Caesar. He said that that was the most unkindest cut of all, namely the one which was given by Brutus, the son of Julius Caesar. But I don't claim that Shakespeare discovered already this theorem, but it might be interesting. No. So we have seen that if you have a single row routing problem from the geometric point of view, and you have a two-layer Manhattan technology, then we can solve the problem in linear time. If we have, by the way, one more interesting question. If we can solve the problem, and we can minimize the width of the solution, then we might be greedy and want to have an even third question, that among all the possible such solutions, which is the one which minimizes the total wire length? And it's easy to see that the horizontal wire sections are given anyhow, only the vertical wire segments must be summed to a minimum number. And you can recognize that this is a special case of another famous graph theory problem, the so-called minimum sum coloring. Coloring simply means that you decompose the vertex set into independent sets, but here you want to minimize instead this sum, the cardinality of the first independent set plus twice the cardinality of the second, etc. And it was conjectured for quite a long time that since interval graphs are so simple, maybe even this problem, which is also empty-complete in general, maybe this problem can also be solved in polynomial time if restricted to interval graphs. But this is not the case. It turned out, one of my former PhD students, Szkaliczki, proved that even for interval graphs, this is an NP-hard problem. His proof is not very beautiful. He actually constructs a three-set type construction, so it's a long and not very pleasing solution. But anyhow, it was a problem which was open for quite a long time, and we were very pleased that he could solve it, and it has been quoted quite a lot of times since that time. Now, all these about the Manhattan technology. What happens if we have the unconstrained two-layer technology? You might expect that sometimes a smaller width is possible because you don't have any constraint. This problem is open as far as I know. Only very sporadic particular results are about that. Nobody knows the complexity, nobody knows the a non-trivial lower bound. Of course, you can say that the minimum width of the Manhattan solution divided by 2 is obviously a lower bound, but nothing much better is known about that. However, I don't want to spend much time about the single row routing problem, because the channel routing is far more important from the point of view of applications. Now, if you are considering channel routing problem in 2 layers, and you formulate it as a decision problem, given the width, and you ask whether it can be solved in that width or not, this problem is amply complete in the Manhattan technology. That was published by Szymanski's paper in '85, but by at that time it was known via discussions and informal reprints for a couple of years. And it's very funny that a year earlier, in 1984, Dave Johnson had an ongoing column in the Journal of Algorithms. This is the same guy who co-authored with Gary the famous book about anti-completeness. He had an ongoing column in Journal of Algorithms, and in '84 he listed the complexity of various VLSI-related problems. He mentioned that Szymanski's result will be published soon about the ampli-completeness of this problem in the Manhattan technology, and he continued in the following way. Our colleagues at Bell Labs, at that time there was a Bell Lab yet, are working hard in proving that it's also ampli-complete in the unconstrained model. Maybe by the time when this article will be published, the proof will be ready. Now, I met Dave Johnson in '91 and asked him whether could they finish already the proof, and they said not yet. So probably even now it's an open problem. Again, we have some partial results on that, but it would be nice to have a reasonable answer to this question in the 2-layer unconstrained model. Once again, all these were for the decision problem if the requested width is given and the answer is yes or no, whether you can do it or not. And there's another problem, a weaker problem, whether you can do it at all. With a larger width, possibly, but what can you do in this case? Now, in this respect, we have more results. First of all, there are unsolvable instances in the 2-layer channel routing problem in the Manhattan model. The simplest one is the following. Suppose that all you have are 2 nets. Net 1 has to be connected from northwest to southeast, and net 2 for the other one. If there is no extra column where the wire segments could make a turn, then this problem is simply unsolvable, because if you start going to the south in net 1, sooner or later you have to use a vertical wire segments, and that blocks everything else. So such a simple problem is simply unsolvable, but I repeat, only in the case if there are no extra further vertical columns. If there is a single one, then you can already solve the problem, maybe in this way or some similar way. And if you understand this observation, you will not be surprised to learn that it's a very easy way to characterize all the unsolvable instances. First of all, a trivial generalization of this 1, 2, 2, 1 thing is that suppose you have n nets, each of them has one terminal on the top, one terminal on the bottom, then essentially you can suppose that the order of the nets is 1 to 2 in the natural order on the top, and arbitrary permutation on the bottom. Now, if this permutation is different from the identical permutation, and you don't have any free column, then you can't solve the problem. That's trivial. And not so trivial, but fairly easy, that everything else can be solved. Another PhD student of mine, Szeszlér, proved this already almost 1.5 decades ago, that this is the only exception. Everything else can be rooted in the 2-layer Manhattan model. As a special, and moreover, it can be done in linear time, and the required width is never more than 75% more than the length of the channel. I don't claim that this is the best solution, only the existence of the solution, and there's a special corollary which is very useful, that if you have a single free column, then you can do everything. Of course, you can also ask the question, what is the situation if we are not in the Manhattan technology, but in the unconstrained 2-layer technology, then everything is solvable. There is no such ugly exceptions. In fact, back in 1990 with a student of mine we could prove that every instance can be solved also in linear time, and the required width of the channel is never more than 50% extra to the length of the channel. And once again, this is not best possible. This is just a simple linear time construction, and I am pretty sure that much better can be arranged. But as far as I know, no interesting result has been found since that time about improving the length. So far, I was only speaking about two-dimensional routing. What does it mean, two-dimensional routing? Whether it was channel routing or switchbox routing, the input is essentially one-dimensional. A sequence of numbers, or 2 or 4 sequence of numbers anyhow, and the output is obviously two-dimensional because we have a plane routing, and the number of layers was typically 1 or 2, or of course there are further results how we can do. I didn't speak about channel routing, which is obviously more difficult than sorry, I didn't speak about switchbox routing, which is obviously more difficult than the channel routing. It contains channel routing as a special case. And all these problems are really hard. So typically a 20 by 20 size switchbox, whether it can be routed on 4 layers or something like that, is hopelessly difficult even now. There is no really good solution for that. Not only are they NP hard, but as far as I know, there is no really effective solution for that. And therefore, it's a very natural question is that saying that why not switch to 3-dimensional routing? Because the technology permits nowadays 4, instead of 4, rather 6 or 8 or even up to 12 layers or something like that. So the number of layers is comparably large to the size of the other 2 dimensions. And therefore, we can put a question like that. Take a cube or a rectangular cuboid where the sides of the cube contains the nets and the terminals, and try to interconnect everything inside this cube or rectangular cuboid. So the output is 3-dimensional. And the number of layers, the 3rd dimension of the cube, can be comparable with the other 2 dimensions. And in this case, the simplest subcase, which corresponds to the single row routing problem, is the so-called single active layer problem, which means that on the base rectangle of the box, you have all the next terminals to be interconnected, and you can use the area over this side to realize everything. And again, the first question is whether you can solve this problem always, or whether there are some unsolvable instances. And of course there are. Here are the simplest one. Suppose again that you have, for example, a 2 by 2 square, and you have to interconnect 1 to 1 and 2 to 2, and all that you can use arbitrarily high part of the 3-dimensional space, but you don't have any way to go right from this or left from this or anything outside. Then obviously you can't solve that, because you start going from this terminal upwards, orthogonal to the basic plane, and in the very moment when you turn to the right or to the south, you will block the second, one of the terminals of the second net. So if you don't have an extra column or row, then again you can't solve that. A similar but somewhat more complicated situation is here. More generally, we could prove that an instance is unsolvable if and only if, and again the other direction is not trivial, all the terminal positions are occupied and no pair of adjacent terminals belong to the same net. This second remark is important, so have a look at this one. Suppose that instead of 4, there were 3 in this position. Then you could interconnect 3 with 3 somewhere, and above that part, you have a lot of infinitely much free space for making all the other tattoos. So it's very important that in this unsolvable instance, any pair of adjacent vertices belong to different nets. That makes it unsolvable. And therefore, one half of this statement is trivial. If all the terminal positions are occupied and no pair of adjacent terminals belong to the same net, then the problem is unsolvable. And it's not very difficult to prove. That's again a result of Szeszlér, my former student, that everything else is solvable. Of course, in practical solutions, engineers do it in a little bit different way. They do allow extra columns and rows. What they call it's a kind of spacing. So if the real terminals are situated in these places, then the dotted lines show extra spacing where you can also route the wires, and then of course you can solve the problem somehow. I will call such a spacing x2 and y2, meaning that both in x direction and in y direction I double the columns. So 2 means one extra line. X or y equals 1 would mean that I don't allow spacing in that direction. Now in this case, we could prove with Szeszlér that if both x and y are at least 2, that means if we allow spacing in both dimensions, then we can solve everything. Moreover, if n by n is the size of the single active layer, then we can do the routing with height less than or equal the number of nets. This is basically trivial, because if you have no better idea, then you simply use an extra level for an extra net, and all that you have to do is making such half-unit steps to avoid crossing. So this is trivial as long as we have height less than or equal n. On the other hand, if we don't allow spacing in both directions, only in one of the directions, then it is still possible to solve, but much, much more complicated. In our construction, we need spacing 8, as high as 8 in the other direction. And the reason of that is that if two lines want to cross each other, which is of course not permitted, you can't always make the detour in the same way, because you don't have spacing in one of the two directions. So probably this picture illustrates that it really needs a more complex construction. Anyhow, it can be done, and again in linear time and linear height. Now, the natural question is whether we can do it in smaller height, because this ordo n square, as a worst case, is pretty bad. And in this direction, there was a result of Agarwal, Kleinberg, and Williamson in 2000. They could solve a very similar problem in ordo n log square n steps, but, sorry, not in that many steps, that many height. But they could do it only in the case if each net contains two terminals only. And we could improve that, first of all, for arbitrary nets, even if they contain more than two terminals, and not in n log square n, but simply in linear way. For this one, we essentially use edge coloring techniques, like the proof of Shannon's theorem for edge coloring of multigraphs and things like that. And of course, there is a further question. Now we know the equivalent of the single row routing problem. That was the single active layer routing problem. The next natural question is the analog of the channel routing problem, which will be the three-dimensional channel routing problem. That you have the cube, and on two opposite sides of the cube are the terminals, and inside the cube you have to make the connections. This again is not always solvable. And the answer to characterize the unsolvable instances is something to do with this very old puzzle, which has been introduced sometimes in late 19th century in the United States. In Hungary, and I think in Europe, it is usually called the 15 puzzle. In America, it is sometimes called Samuel's puzzle, which was a very popular puzzle in the late 19th century. I heard that once it did happen that the train from New York to Washington didn't stop at the station in Baltimore because the locomotive driver was playing this and simply forgot to stop at the station. Whether it is true or not, I don't know. Anyhow, probably all of you have tried this 15 puzzle, and it's very easy to start and doing it for the first couple of steps, and at the end, you either get the good solution, or you reach something like the second one, where everything is okay instead of a single inversion. And it's very easy to prove that the second one is unsolvable, and essentially only the parity of these inversions decides whether a problem is solvable or not. This is a sort of well-known result since long time. And what David Szeszlér and one of his students could prove in 2005 is that in case if no subdivision is permitted, that means if both x and y are 1, then the only unsolvable problems are if the two sides are separate, then everything is, then something is solvable if and only if the two sides are separately solvable and it is not like the 15 puzzle. This is a simplified way of formulating it. So this is the answer for the solvability question. And if this property is satisfied, then they succeeded to give an algorithm with subdivision. And for every case, even for this case, if the subdivision is 2 in both dimensions, then they could solve it so that both the height is linear and the time almost linear, where capital A is the size of the input, which is in the worst case n squared if everything is covered. Well, I think that's enough for this area, and я благодарю за внимание.
Спасибо большое. Questions? Comments? No questions and no comments.
Excuse me, for the three-dimensional case, are they currently applications for the three-dimensional case? Because in two-dimensional, we use it in electric circuits.
So for the three-dimensional case, whether
In the two-dimensional case, there is application in electrical circuits, as you mentioned. Are they currently applications for three-dimensional case?
very little. So actually, I provide one or two references in electrical engineering journals that they actually use this third dimension in this sense, but most of them don't use it yet. The problem is that technology is developing too quickly. There are so many layers available that even a simple greedy technique, if 2 layers are not enough, we take 4 layers. If that's not enough, we take 6 layers. And in most of the cases, they can solve it before the limits of the technology by now.
So when you use vias, is the problem three-dimensional?
When you use
The holes to connect layers. Vias.
not necessarily, it depends how you define it. In the layer technology, which is, I think, more than 50 years old by now, the vias were always considered as via holes.
Yes.
But in modern technology, we permit that a via is going just from one layer to the next one, and the same area can be used by different lenses later. That's how the technology actually works.
Thank you very much.